Well, now let's tip the circle on its edge. Instead of having a circle that spins around horizontally with no gravity affecting it, let's take a look at motion in a vertical circle. So gravity is affecting this object here as it goes around this circle. Let's think about what that does to the object that's spinning in a circle. Remember, gravitational force is always directed downward. So as it goes around the arc, it's always being pulled downward at the bottom, at the right-hand side, and all the way back up to the top. We notice that there's a change in the speed. As we went around that loop, it started out slow. In fact, at the top of the arc, at the very top of the arc, it's at its lowest velocity that you have. And when it got around to the bottom, because it was accelerated all the way down, we reached maximum velocity. And then in between, it was speeding up as it went down here and slowing down as it went up here, because gravity was always acting downward. Here that helped make it faster. Here that helped slow it down. Well, since centripetal force is the net force acting towards the center of the circle, let's take a look at what's going on at the top of the arc. At the top of the arc, you have two forces that are acting towards the center of the circle. So here's the object. One of the forces that's acting towards the center of the circle is the tension in the string, Ft I'll call it. But the other force that's acting towards the center of the circle when it's at the top of the arc is gravity, the weight, the force due to gravity, or the weight. Both of these together are what make up the centripetal force. So since centripetal force is the net force acting towards the center of the circle, Fc is equal to the tension in the string plus the weight. But we know that centripetal force is equal to m times v squared divided by r. And the v that we're talking about here is the v at the top of the circle, which is v min, the minimum speed. And so we can calculate the centripetal force here. If we knew the centripetal force or the velocity, mass, and radius, we could also use that to calculate the tension. At the top of the arc, the string tension is at its minimum. So we know that force of tension plus gravity, the force of weight, Fg or Fw, is equal to the centripetal force. So that means the tension, when it's at this lowest point, at the minimum point at the top of the arc, well, that's going to be equal to centripetal force minus the weight. At the top of the arc, there is a speed, the minimum speed that you have to keep this thing moving at in order to keep the string tight and keep this thing moving in a circle. If you've ever spun a thing around in a vertical circle like this, you know this from experience. You can spin it around and it'll keep going unless you slow it down. And you get it down slow enough to a certain point where it just won't make the arc anymore. And we want to know what is that minimum speed to keep this from happening. That's our objective here. So let's think about that. At the top, we know that the centripetal force is equal to the force of tension plus the weight, the force due to its weight, or the force due to gravity. Now, if we got to the point where the string has just lost its tautness, that means this force would go to zero. And that would represent the point where you just have crossed the line from being able to make the thing spin, keep string tension, and not. So this represents a sort of minimum speed, or what we call the critical velocity. Well, let's try and figure out what this means. The force of weight, well, that's equal to mg. And that's now equal to centripetal force, which is mv squared over r. So these two things, set equal to each other, provide us with a way to figure out what is this critical speed, that minimum speed that you have to keep moving at to cause this thing to stay taut. Here's how this works. Mass drops out, so it turns out it doesn't really matter if you have a heavy object or a light object. It only matters what the velocity is and the radius, assuming that g remains constant. So let's solve this for v crit. The critical velocity squared is equal to g times r. So that means critical velocity is just equal to the square root of g times r, or r times g. So that's something that might be useful to put in the toolbox, because this allows you to calculate minimum speeds needed to keep the string taut. Well, let's try this one. An 85-gram yo-yo, same yo-yo from the last problem, spun in a vertical circle. What's the minimum velocity needed to make this happen? Well, that'd be the v crit, the critical velocity. Well, we found that the critical velocity is just the square root of r times g. Let's assume that it's the same vertical circle we had before, and that circle was 0.75 meters. So we'll plug that in here for radius, 0.75 meters, and it's happening on Earth, let's say, so 9.80 meters per second squared is the acceleration due to gravity, and then we can find our critical speed here. Let's make sure the units work out right. Meters squared over seconds squared, the square root of that would be, in fact, meters per second. Now, if you do your calculations, here's what you find out the units come out, or the numbers come out to, 2.71 meters per second. So if you go slower than 2.71 meters per second, the thing's going to stall out and it won't be able to make the circle. Let's take a look at the free body diagram at the bottom of the arc. Now the object is sitting down here at the bottom. Tension is acting towards the center of the rotation because this thing is spinning like this, but now the weight is acting downward. So the centripetal force in this situation, remember centripetal force is the net force toward the center of the circle, that's going to be the tension minus the weight. So that would mean that the tension here is going to be equal to the centripetal force plus the weight. That's the maximum tension that you're going to get. And the centripetal force plus the weight is equal to that maximum tension. String tension is maximum at the bottom of the arc. We know that centripetal force plus the weight is what string tension is equal to. So let's just plug those both in there. mv max squared, because the maximum velocity occurs at the bottom of the arc, divided by r, that's our centripetal force, plus the weight, and the weight is just mg. So this gives us a way to solve for what's the maximum tension that you could get at the bottom of the arc. Well, here's an example problem that might make use of this knowledge. Same yo-yo, 85-gram yo-yo, same radius, it's spinning in a vertical circle. Question here is, what is the tension at the bottom of the circle? That's what we're trying to find. Maximum velocity is given to us as 5.5 meters per second. Okay, well, let's lay out this problem. We're at the bottom of the circle, so that means we've got this situation where we've got force tension going up, we've got force of weight going down, so that means the centripetal force is equal to the net force towards the center of the circle, and that's Ft minus Fw. So the tension, which is what we're trying to find here, solving this equation for that, would be Fc plus Fw. And the centripetal force is mv squared over r, and the weight for things in a gravitational field is mg. So we can rewrite this and we can say the tension here is going to be equal to the mass times v squared over r plus g. Well, now let's plug some stuff in here. The mass of this object, remember this yo-yo, is 0.085 kilograms. The velocity, Vmax here, was 5.5 meters per second, and that's going to be squared. The radius of the circle is 0.75 meters, and then g is 9.80 meters per second squared. Well, let's collapse this down a little bit here and look at the units. If I take meters per second and squared, I get meters squared per second squared. But then if I cancel a meter out of there, I've got just meters per second squared. When I add that to acceleration due to gravity, I have an acceleration. Meters per second squared times kilograms, well, that's going to end up being newtons. When you do the actual arithmetic, you find out that the answer is 4.26 newtons. So that's the tension in this object. Well, here's a problem that allows us to work in some stuff we learned from before, like coefficient of friction, to some of the new stuff here about rotational motion. We got a car that's going around a curve. So the car moves around a curve like this, and something keeps it from sliding off. And we all know that it's friction between the tires and the road. If you don't have good friction between your tires and the road, you're going to slide off. Coefficient of friction goes down because it's icy or rainy or your tires are just really bad. Well, then what will happen is you'll slide off the side. So it has something to do with coefficient of friction. Well, the curve, here are the characteristics of it. It has a radius of 50 meters. So you're going around in a circle. That's circular motion. And we know coefficient of friction is 0.625. The car has a mass of 1,200 kilograms. So that's going to have something to do with its normal force. Plus, It's the object now that's spinning around in a circle. It's not on a string, but it's still doing circular motion. The question is, what's the highest speed that you could hit before you start sliding off the road? Now, if you were a highway engineer and you're going to post a sign telling people how fast they should go around a curve, this is probably a calculation that you'd have to do to figure that out. Let's take two views of this thing. First of all, let's look at it from above. We know a couple of facts here. We know that this is 50 meters. We know that the car is moving around this circle. It wants to slide off or fly off the road because its velocity is in this direction. But of course, it's being accelerated towards the center constantly, always moving towards the center. And the reason it's moving towards the center is because of centripetal force. So there's some force, some FC that's pulling it in here. Well, if you think about the car from a different view, here's the flat road. Here's the car sitting there, tire, car, back window. So we're looking at the back bumper here. I know my picture doesn't look that way, but we are. And if you think about the free body diagram, we've got a normal force from the weight of the car. It's just the weight. We've got a vertical force, and that's just a restorative force. And then the only other force that's acting here is the force of friction, which is actually acting here and here to keep the car from sliding off the road. Well, that force of friction is the centripetal force as well. That is what makes it go in a circle. So, if the frictional force is equal to the centripetal force, and we know that centripetal force is equal to m times v squared divided by r, well, then we have something to go on. We can make a new equation here that says force of friction is equal to m times v squared over r. But thinking about what force of friction really is, force of friction is mu times force normal. But force normal is m times g. So let's take all that information and put it together. Force of friction is really mu times force normal, but force normal is m times g. So the force of friction is mu times m times g. But that's also equal to the force centripetal here. And centripetal force is mv squared divided by r. So it turns out that mass doesn't matter. And so that's why the highway engineer can post a sign up there that says, don't take this curve at faster than 35 miles an hour. It doesn't have to say, if you're a truck, you can go this fast. If you're a car, you can go this fast. If you're a motorcycle, you can go this fast. It doesn't matter. Mass drops out of here. The same safety speed is true for every vehicle because it doesn't matter how much it weighs. What we're trying to get at here is what is the maximum speed that we can do this at. So we're trying to solve this for v. So let's solve this equation for v. Mu times r times g would be equal to v squared. So if we take the square root of both sides, here's what we find. Velocity, maximum speed here that we're trying to find, is the square root of mu times r times g. Let's plug our numbers in. The coefficient of friction for this particular problem is 0.645, they said. The radius is a 50-meter radius for this curve. And gravitational acceleration, as always, 9.80 meters per square second. Checking units. I got meters times meters, that's meters squared, divided by seconds squared. Well, when I take the square root of that, I'm going to get a nice speed unit, meters per second. When I do the arithmetic, I find out that 18 meters per second is as fast as you can go.